Because so first of all, whenever you are considering numerical calculation, the complexity is what should be the size of data, how the data to be imported, and after the data is being imported, how it is processed, and how we are getting the output or the result. So the entire process we are saying to be computational numeric. So right now, as we are considering error, numerical error. Generally, first of all, whenever we are considering numerical error, first of all, we must think how the numerical data can be represented to the computing device. Normally, you are operating a calculator for the computational purpose, or you are using a digital computer. So whenever we are thinking to import the data, so first of all, data representation is the most vital factor. How are representing the data? Data can be represented by three ways. What are the three ways? First one is fixed point form. Another one is floating point form. And another one is scientific form of representation. So what is fixed point of representation form? Here, in case of fixed point representation form, the number of decimal digits are fixed by the device. So then question arises, what are decimal digits? As you know, from 0 to 9, there are how many decimal digits? 10 number of decimal numbers are there. So that in order to form a data to be inputted, how many these numbers are required or how many numbers are intended. Okay. So here, in case of fixed point representation form, the device has certainly been fixed by some decimal digits. It may be 4 decimal digits, it may be 5 decimal digits, or it may be 6 decimal digits, or so on and so forth. So by virtue of that, whenever nowadays we are just computing very huge data or very small data. So whenever we are using or inputting a very huge data, what will happen? As the size of the data is fixed by the manufacturer. If your data size is very big, so that some part will be deleted. If some part will be deleted, so error will be computed in that purpose, or error will be there. So in order to overcome this problem, nowadays we are using floating point representation form. What is floating point representation form? So in case of floating point representation form, here the number of decimal places are fixed. Up to 3 decimal places or up to 4 decimal places. The device are being fixed with that one. Okay. So that as this one is floating point representation, whatever a bigger number is there, we can convert that one to the standardized floating point form, how much big it may be, and the process is known to be your normalization. So what is normalization? Normalization is a process for converting a very big data to floating point representation form. and the process is known to be your normalization. Here, the general form of representation of the floating point is plus or minus of m into 10 to the power of plus or minus of e. So what this m represents? Mantissa. This m represents, so again I am repeating, the standard form of representation of a data in floating point representation is plus or minus of m into 10 to the power of plus or minus of e. So what is this m? M represents mantissa, whose value is strictly less than 1 and whose value is greater than 0. Strictly less than. I am not saying less than or equal to. It should be 0.9, 0.999, 0.959 or 69 according to this one, but it cannot be 1. Okay. And then 10 is your base, that is numerical base. And what is E? E is your exponent. And the value of the exponent normally we are saying ranges in between 32 plus 32 or minus 32. But nowadays digital computers allowing much more than that one. Okay. So that the standard form of representation of this one. So any number given, maybe a very huge number or maybe a very small number. By the process of normalization, we can convert this one to floating point form. So as it is converted to floating point form, the standardized form, the normalized form, then we can input the data accordingly, and then the corresponding and the required output can be calculated without any error or with a very small with a very small amount of error communication or very small amount of error. Okay. So how you are converting a general number to this floating point form? Let us consider some example in this regard. 99, then 375 is there. 99,375. As for this one, this should be converted to the floating point form by the process of normalization. So you see, if I am multiplying here 10 to the power of 5 and divide here 10 to the power of 5, can I write this one to be 0.99375 into 10 to the power of 5? Okay. So this 0.99375 is your mantissa, and this plus 10 to the power of 5 means 10 is your base, 5 is your exponent. Like thus, let us consider a number is given 0.1030 then 375. How I can convert this one to floating point form? If I will multiply here 10 to the power of 3 and divide here 10 to the power of 3, the resulting value I can write here 0.375 into 10 to the power of minus 3. So is it satisfying the characteristic of floating point or not? Here 0.375 is your mantissa, is your mantissa, and this minus 3 is your exponent, and the process is known to be your normalization. Okay. Like thus, let us consider I am writing 1.0037. If I just want to convert this one to floating point representation form, so if I multiply here 10 and divide here 10.
सर से बोर्ड टा देखिए होती
ମୁଁ ପଠେଇ ଦେବି ବାବୁ।
ଆଜ୍ଞା ଆଜ୍ଞା
ମୁଁ ପଠେଇଦେବି, କେବଳ ଟିକେ ଭଲ ଭାବରେ ଶୁଣ ହେଲା କି, ଯେତିକି ଲେଖିପାରୁଛ ଲେଖିପାର, ଅଦରୱାଇଜ ମୁଁ ତମ ପାଖକୁ ଏଇଟା ପଠେଇଦେବି ହେଲା। ଏବେ ଦେଖାଯାଉଛି କି ବୋର୍ଡଟା?
ନାଇଁ ସାର୍ ନା ସାର୍ ସାର୍ ବ୍ୟାକ୍ କ୍ୟାମେରାଟା ସାର୍ ବ୍ୟାକ୍ କରିଦେଲେ କ୍ୟାମେରାଟା ଫେସ୍ ଟୁ ସେଟା ବୋର୍ଡ ଦେଖାହବ।
ବ୍ୟାକ୍ କ୍ୟାମେରା କେମିତି?
କ୍ୟାମେରାଟା ସାର୍ କ୍ୟାମେରାକୁ ସାର୍ ଟଚ୍ କରିଦିଅନ୍ତୁ, ସେଟା କ୍ୟାମେରା ଯୋଉଠି ଅଛି ସେଇଟା ଟଚ୍ କରିଦିଅନ୍ତୁ, ସେଟା ବ୍ୟାକ୍ ହେଇଯିବ। ସେଟା ଫେସ୍ କ୍ୟାମେରାଟା ଅଛି।
ଦେଖିଲେ
ସାର୍
ଦେଖାଯାଉଛି କି?
ଆଜ୍ଞା ଆଜ୍ଞା ସାର୍, ହଁ ସାର୍, ହଁ
ଆଚ୍ଛା।
ସାର୍ ଦେଖାହେଲା।
So if I'm multiplying here 10 and dividing here 10, okay, ଏବେ ଦେଖାଗଲା ତ କିଛି କାଂଶରେ?
Yes sir.
By multiplying and by dividing, the number remains same, so that I can write this one as 0.1037 into 10 to the power of 1, so that this 0.10037 is our mantissa and 10 to the power of 1, so 1 becomes the exponent part. Okay, so by virtue of this process, that is normalization, we can able to convert any big number or any huge number to the standardized floating point form, and also a very small number also to the standardized. By this process we can able to standardize to floating point form, so that the data size becomes compact for our next processing or next processing. Then question arises, what is scientific representation form? The scientific representation form is very similar to this form. There the scientific representation form is also plus or minus of m into 10 to the power of plus or minus of e. So m is also known to be the mantissa and e is known to be the exponent. But here the mantissa value ranges in between 1 to 10. Value of mantissa m is strictly less than 10. It can be 9.999, but it is strictly greater than 1. Okay, so the only difference is the value of m mantissa ranges in between 1 to 10, and the exponent part is also fixed by the manufacturer. As it has been restricted in 4th generation, it has been restricted to 32. Now the digital computers allows the value of e to be up to 302. Okay, next, whenever we are considering the representation, then also we are getting, by virtue of this representation, then as the size of the data is being fixed by the computer, we are getting certain amount of error here. So what is that? One type of error we are getting known to be oversize, and another one is your undersize. What is oversize and what is undersize error? Well, let us consider whatever the data we are inputting in the computer or calculational device. If it is very big in comparison to the standard one. Standard one means fixed by the manufacturer. So what will be there? Automatically the computer will halt, or the computing device will halt, simply writing a error. That means at that extent we have to understand the data size whatever we have inputted, that is very big in the normal representation or normal acceptance form of the device. Okay, and whenever the data is very small as desired by the device, So at that extent, the calculational device will show you syntax error. Syntax error. So at that time, we have to understood that the data that we have inputted is very, very less as per the requirement of the calculational device. Okay. Next question arises whenever we are importing certain data, we are getting certain errors. And these errors are, so first I am saying errors. What are these? First of all, what are the source of error? Whatever the source, where you are getting the error. Generally, the source of error we are saying, first we are getting error from imputation. That is most important factor. Most of the times you are getting a question, what are source of error? That is first part is imputation of data. Second part is algorithm. Third one is output. These are the three major sources where you are getting error. What are they? First one is imputation of data. Second one is the algorithm. Third one is output, or we can say computational output. Process of computational output. Process of computational output. So somehow whenever we are inputting certain data, if the size of the data is big, or if we are inputting certain data wrongly, so in calculation process you will get a wrong error. So that is the first source of error in computation. Second one is, in case of, let us consider we are getting iterative calculations. Iterative calculation means repeated calculations. But repeated calculation requires loops or stepwise calculations. But let us consider the loop whatever you have used in an algorithm, that is not sufficient. So after finite number of steps, let us consider it will go out of the calculations. So normally after finite number of steps, whatever the result we must get, that is not the accurate result or actual value. So we are getting certain error. Next one is process of computation. What is the process? Let us consider we are calculating or we are just using certain process for solving a equation. Okay. So solving a equation, there are different approach. So out of those many approaches, so certainly there must be one approach by using which we can get minimal error. So if you are using some other procedure, as for example, solving a equation, there are several methods like transcendental equation, I am saying, bisection method, Newton-Raphson's method, second method, regular-Folsey method, Muller's method. There are a lot of methods. But if the initial approximate value or initial value is very close to the real root, and if you are choosing Newton-Raphson method, so that we'll get the most accurate output or most accurate result. In that sense, if you are using some other methods, after those number of steps, you will get error. So that the process of the third one is, in case of computation or computational approach for finding the output, we are also getting certain amount of error because of choosing the particular or acceptable computational process, we are getting error. So this is known to be process of computational output. So these are the three major source for finding the source of error. Okay. Next part is, as you are saying, imputation of data. Next, first I am considering imputation of data. So when we are inputting certain data, how we are getting error? So let us consider some errors. For that reason, I am writing general errors. So what are general errors? Let us consider, I am giving a small example. Let us consider we are calculating in a physical experiment, we are calculating the value of G, gravitational force of attraction. Okay. In Bhubaneswar, the value of G is given to be 9.81. Okay. And we are using some particular method like maybe bar pendulum or cutter's pendulum. We are calculating, taking some or LT square graph. We are just trying to calculate the value of G. So normally, let us consider by calculational process, I am getting a value that is G dash, that is to be 9.8 or 9.79, let us consider. So the original value is 9.81, that is the standardized value or standard value in Bhubaneswar. But by using some physical experiment and different approach, we have got the value to be 9.79. So we have got this one as your calculated value. 9.79 is your calculated value or computational value or experimental value. And now 9.81 is our standard value. So now we are getting error. So if I am getting this one to be exact value is your X and 9.79 is your XA or XC. So exact is X and calculated value is your XC or XA. So that are they are same? Not at all. So what is the difference between them is known to be the error or general error. So that I can write here error is equal to X minus of XA. But generally in this particular case I have found the observed value or experimental value is less than the exact value or standard value. In some cases the calculated value may exceed to the standard value. That means we'll get here negative. X minus of XA can be negative. But always keep it in mind, error cannot be negative. Error cannot be negative at all. At that extent, we are writing absolute, we are finding absolute error. That is written to be E bar modulus of E or ABS E. That is simply required. That is absolute value of X minus of XA. Depending upon this value, we can able to find another error that is known to be a relative error. That is denoted by your ER. That is absolute error divided by exact value or the standard value. Okay. Depending upon the relative error, we are getting percentage of error. That is known to be your percentile error. So that is ER means relative error multiplied by 100. Okay. So this happens to be the general error calculational approach. But then question arises, as I have simply said, how we are calculating or how we are getting general errors. So errors we are getting by different approach. Errors we are getting by different approach. What are the different approach? First of all, errors you are getting by round off, known to be rounding error. So what is rounding error? Let us consider your calculational device is fixed up to 5s. 5 then capital S. So what this 5s denotes? 5 then capital S. So what this 5s represents? 5 significant digits. In some books also it is written 5SD, means 5 significant digits. Either it can be written as capital S or it can be written as 5SD or 6SD, anything else. So whenever we are saying that a number to be rounded off up to 5 significant digits. So already I have said what are significant digits. So always keep it in our mind that the decimal digits that are required to form a number are known to be significant digits. What are the decimal digits? There are 0 to 9. All totally there are 10 number of decimal digits are there. And in order to form a number, how many decimal digits are required that are known to be the significant digits? Let us consider, as for example, I am saying 10.025. So in order to represent the number, how many significant digits are required? How many significant digits are there? 5 number of significant digits. If I am taking 0.00325, so what is the number of significant digits? 3 significant digits are there. If I am writing 9.925, what is the number of significant digits? 4 number of significant digits. You just consider these 3 examples. As I have written here, 10.025. I have said it has 5 significant digits. 0.00325. There are 3 significant digits. 9.925. I have said there are 4 number of significant digits. Then question arises in the second example. 0 is a decimal digit. It is also used for framing that number. Why the number of digits? Why the number of significant digits are 3? And in case of first one, there are also 2 digits. 2 zeros are used. Why the number of significant digits are 5? Always keep it in your mind that whatever the 2 zeros in the first example I have given, they are in between 1 and 2. That implies after, if I am converting the second one, try to write the second one to standardized form, first one to the standardized floating point form. So this will give you 0.10025 into 10 to the power of minus 2. 10 to the power of plus 2. If I am converting this one, second one to standardized form, you are getting 0.325 into 10 to the power of minus 2. Yes or no? And if I am converting the third example, I am getting 0.9925 into 10 to the power of 1. Now we can just go on calculation. How many digits are required? In the first one, are you getting 5 number of digits or not? In the second one, are you getting 3 number of decimal digits to form this number or not? So that we can get a confirmation that whenever zeros are in between any other decimal digits, they are significant, and whenever they are before any number, they are non-significant. Here you can just see 00, then 325. So that after 0, before 0, there is no such number. And then decimal point. So these two zeros are non-significant. This is not significant. But if I'm writing here 9.500, can you say how many significant digits are there? 4 significant digits are there. Why? Because after decimal point, we are getting 9500 into 10 to the power of 1. So that how many decimal digits we have got here? 4 number of 9 is a 1, 5 is second one, 0 is third one, another 0 is the fourth one. So these are 4 number of decimal digits are required. So from this one we can able to say the decimal, or we can say 0 after the decimal point are significant if it precedes any values, any decimal digits, and when it doesn't precede any numerical digit, it is not significant. Okay. Now let us consider these are the numbers that we have got. Am I clear of this one? Then let us consider the next concept, that is how we're getting or how we're rounding a number. Let us consider your device is confirmed by 3 significant digits. Let us consider by 4 significant digits. So we have to maintain or we have to convert the data. These are the data. These are to be maintained by this format. So we are just counting one by one. So in the first example, you see, I am counting. So this is my first significant digit, second significant digit, third significant digit, then fourth one. So I must confine this one up to this. So we have to discard some part. But discarding a part, there is certain rule. So that is known to be your rounded off principle or rounding principle. So what is rounding principle? Let us consider we want to round a number up to n significant digits. Then we are checking the n plus o, we are checking the n plus of 1th digit. So this n plus of 1th digit, it can be greater than 1, greater than 5. It can be less than 5. It can be equal to 5. There are 3 possibilities are there. If the n plus of 1th digit is greater than 5, then add 1 to the nth digit. Okay. And if it is less than 5, n plus of 1th digit is less than 5, then the nth digit remains same. There will be no change to the nth digit. If the n plus of 1, the last possibility is it can be equal to 5. If it is equal to 5, then what will happen? Then check the nth digit, if even, remains same. If odd, add 1. Okay, this is the principle for rounding a number up to certain significant digits. So what is the principle? Let us consider we want to round a number up to n significant digits. So we are checking the n plus of 1th digit. If it is greater than 5, then add 1 to the nth digit. If it is less than 5, then the nth digit will remain as it is. If it is equal to 1, then we are checking the nth digit. If it is odd, we are adding 1. If it is even, then it will remain as it is. Okay. So let us consider now. To some extent, I am taking some examples. Let us consider this is 0.993572 into 10 to the power of 3. Another one I am taking 0.17329 into 10 to the power of minus 2. Third one I am getting 0.32795 into 10. Okay. So let us consider I am wanting to round up these numbers by 4s. And another two examples also I am taking 0.72545 into 10 to the power of minus 2. And another one I am taking 0.113057 into 10 to the power of 5. Let us consider the first one. So 99352. So here I must go on counting one by one. So 9, first number, second number 9, third number 3, fifth. Then what is your n plus of 1th digit? 7th, which is greater than 1. So what will be? This will be rounded to 0.9936 into 10 to the power of 3. Okay. Am I clear? So here n plus of 1th digit, your 5th digit, which is 7, that is greater than 5. That's why we are adding 1 to the nth digit. So 5 plus 1 is 6. So this becomes 0.9936 into 10 to the power of 3. There is no change to the exponent part, only the mantissa part to be rounded. So in the second case, we can just see 1 is your first digit, 7 is your second digit, 3 is your third digit, 2 is your fourth digit. So fifth digit is your 9, which is greater than 5. So that this number to be rounded to 0.1733 into 10 to the power of minus 3. Likewise, you can just see the third one, that is 0.32795 into 10. So what is your fifth digit? That is 5. So third case is there. As it is equal to 5, we have to check the nth digit, means fourth digit. As it is 9, which is a odd number. So this number should be written as 0.3280 because 1 to be added here into 10 to the power of 1. In the third one also, sorry, fourth one also, you can see what is our fifth digit? 5. So as here 0. So directly we can write 0.1131 into 10 to the power of 5. Likewise, like this, you can also say, what will be the next one? 0.72545. So as here, the fifth one is fifth digit is 5. But the previous one, is an even number, so that this will be same to be 0.7254 into 10 to the power of minus 2. Okay. So by rounding, we are getting, by rounding, are you getting the same number? In some cases, you can get the same number, but in most of the cases, we are getting some different number. Maybe to certain decimal extent, but that certain decimal extent is our error. So that whatever the error we are getting from the exact value, if we are subtracting, we are getting the error, and that error is known to be the rounding error or rounded off error. So here this one is your exact value. This one is your the value after rounded off. So the difference between these two, we are getting error, and that is known to be your rounded off error. Okay. Then most of the times you are getting a short question, that is standardized question also. That question I am writing here. Sometimes the question setter asks when a number is rounded up to n significant digits, what is the error? Okay. What is the error means what is the absolute error? So it is a general question. When a number is rounded up to NSD, NSD means n significant digits. What is the absolute error? Or what is the standard error also sometimes? Some ask what is the standard error? Just think of this. How what will be the standard error? Because if you'll just see here, by subtracting whatever the error we are getting, so that will take the form, that is 1 by 2 into 10 to the power of 1 minus of n. Or you can say 1 by 2 into base to the power of 1 minus of n. So how? You can just see in the first example. So how many digits are there? 1, 2, 3, 4, 5, 6. But we are rounding up to 4 significant digits. So that whatever the error you are getting, that will give you up to 3 digits, 3 significant digits. Because there is certain changes to fourth, not up to 3. So whatever the changes you are getting, that will give you 1 minus of 4. That means up to minus 3. So it's the answer to this part is 1 by 2 into 10 to the power of 1 minus of n. Okay. So this is the answer to this part. Try to keep this one in your mind, because this is the standard short question. Okay. It will give a particular number, and it will ask you to, it will carry 2 marks. It will ask you what will be the standard error and when it is. So don't go for rounding that one. Don't go for subtracting that one. Directly give your answer. The standard error is nothing but 1 by 2 into 10 to the power of 1 minus of whatever the number is given. Up to which extent this should be rounded. That will be the answer. Okay. So now shifting the another type of error, that is known to be your truncational error. Better I am writing chopping error first, then truncational chopping error. So what do you mean by chopping? Discarding a part without any notice. Discarding a part. That implies No, there is no certain principle. There is no certain principle or no certain rules are there as you have got in rounded up error. There is no certain rules. Simply, we are discarding a part. Let us consider, I am saying, the first example what I have taken, 0.9937, sorry, 3572 into 10 to the power of 3. And if it is given up to 4s and by chopping. So chopping, in case of round up errors, you are just thinking, what is the fifth, what is the fifth digit? Then you are checking whether it is greater than 5 or less than 5 or equal to 5. Then accordingly you are applying certain rules. But here, without considering any rules, we are simply discarding this part. So we are simply writing this is 0.9935 into 10 to the power of 3. Without any applying any rule, we are simply discarding the fifth one and rest one if remains. There is no certain bar and bound, or there is no certain rules. And like this, if I am taking, let us consider point, the last one, 0.72545 into 10 to the power of minus 2. Okay. If I am taking, considering up to 4s, so this will be 0.7254. We are not thinking into 10 to the power of minus 2. We are not thinking what is the fifth digit or what is the sixth digit. We are not simply thinking of it. We are simply writing 0.7254. Okay. So chopping means discarding a particular part of the data or output without applying any rule. Okay. So by this way also we are getting certain errors, and that error, by cancelling or discarding a particular part, we are getting whatever the error we are getting, that error is known to be the chopping error. Like thus, in numerical, getting certain numerical value in decimal representation, we can chop something and we are getting certain error, that we are saying chopping error. Again, we can just say, same thing. Whenever you are getting a series, maybe exponential series, logarithmic series, or any algebraic series, and at that extent, we're just trying to find, let us consider someone is asking to find e to the power of 0.25. So then, we're applying certain principle and we just want to find what is the expression of e to the power of x. So as you know, e to the power of x is nothing but summation x to the power of n divided by factorial n, where n starts from 0 to 1. So that we can able to write here 1 plus x square by factorial 2 plus x cube by factorial 3 plus so on and so forth. But as here we are getting 0.25. So finding x square is, it is up to the mark, but finding x cube, it will be difficult. Maybe you are using calculator, and then finding x cube for a very small number and again dividing by 6. Factorial 3 means 6. So we are getting certain problem. For that reason, we want to discard the last part, means next part, x to the power of 4 divided by factorial 4 and all others. So discarding a part of the series, certainly we cannot able to find directly the value of e to the power of 0.25, that which happens to be exact. So we are getting an approximate value. By discarding a particular part or a part of a series, we are committing certain amount of error, and that error is known to be truncational error. So The same concept what you are just trying to apply for chopping a numerical data. In case of series expansion, for calculational point of view, as you are discarding part of a series, that's why we are getting error. So that error is known to be a truncational error. Okay. The next error we are getting truncational error. So truncational error is due to discarding a part of the series. Okay. Then the next one is also we are getting error that is known to be significant error. So what is significant error? This significant error is due to, this is simply is due to loss of significant digits. This is due to loss of significant digits. What do you mean by loss of significant digits? Let us consider an example. A question is given like this: solve the quadratic equation that is x square minus of 40x plus 1 equal to 0. Okay. So this equation is given. If I want to solve it as it is a quadratic equation, so I can able to solve x equal to minus of b plus minus of b square minus 4 into a into c divided by 2a. So if I'm solving this one, I am getting 40 plus or minus of 1600 minus of 4. This one square root divided by 2. So that you will get the first x1 means first root you are getting 40 plus 1596. This one square root by 2. And the other one you are getting x2, that is 40 minus square root of 1596 divided by 2. So in case of plus, there is no such difficulty or there is no such problem for finding any error. But for second one, you are getting these two. 40 minus 15 square root of 15.96 whose square root is 39 point around 98 or like that. So that here you are getting 40 39.9597 like this. But here you are getting, are you getting very small value or not? So whatever the small value you will get, it will contain less amount of significant digit. Although the process of calculation is quite good or the process of calculation is utmost right. There is no mistake at all. But still then we are getting certain error. So whatever the error you are getting, that is because of less number of significant digits in the second root. So how this can be avoided? We have to take some alternative approach. What are the alternative approach that we can take? As you know, the product of two roots x1 into x2 is how much? Minus of c by a, c by a. What is c? Because the standard form of the equation is ax square plus or plus bx plus c. So here c equal to 1, also a equal to 1. So that the value of x2 will be simply 1 divided by x2. So finding x2 by this approach, you might get certain less amount of error. Or we can say the significant error or the loss of significant digits can be, to certain extent, it can be managed or it will be less. Okay. So that this is also an important concept. So by virtue of these concepts, we can able to minimize the error. But generally, in numerical methods, error is due to by two. First one is operand, second one is operator. Okay. What are the operands? Operands are all these principles. And what is the operator? The person or the concern who is inputting the data before computation. Okay. This is all about today. I'll just send you this one if you are intending. Or shall I proceed right now to some extent? Hello, Chinmay.
Sir,
Yes. Any concern?
no,
Hello.
no, sir.
Then we'll proceed to the solution. Better do one thing. Go on reading all these things, come with a doubt that will be easier to access. Because if I'll go one by one, it will take sufficient time. But time is not sufficient at all. So tomorrow, what you are thinking to proceed? Shall I go through that solution of roots or your doubts like interpolation or probability or statistics? Which one you are intending?
Sir, solution.
Hmm?
Sir, bas, sir, point.
Because each and everyone you are getting from each and every part, from statistics you are getting question, from probability you are getting questions. So which part you are intending to get more? Hello,
Sir, sir, statistic.
statistics. Okay, tomorrow we'll go through statistics. Statistics means which part you are intending? That correlation, regression, all these things.
All these.
Okay, okay. Tomorrow we'll go through that part. Okay, not worry.
Yes.
Okay, thank you, one. Shall I send this paper?
Sir,
Okay, okay. I'm sending to Vijay and he will send you to all. Okay.
yes, sir.